episode of Voice of the Sea. We're talking to scientists as they prepare to depart on the first leg of the Exports research cruise to the northeastern Pacific Ocean. Exports is a revolutionary scientific undertaking by NASA and the National Science Foundation to understand and predict the flow of carbon through the ocean food web. Planning for the expedition has been going on for over a decade to coordinate hundreds of scientists, satellites, remote underwater vehicles, and 2 research vessels. We start off talking to Exports science leader David Siegel and University of Miami researcher Hillary Close. Describe your role for me.
I am officially the science lead of the NASA field campaign. It's my job to kind of get people to think about what they can do synthetically. And so it's really about how can we predict how much of that net primary production energy that phytoplankton do, how much of that photosynthetic production gets out from the euphotic zone into the interior, and how far deep does it go? What is the team that needs to be assembled to do that? So you have to build this super team of superstars in some sense that can go after this problem. We have unbelievable potential to change ocean optics, change genomics, change how we do things.
We're here in a hangar on the Sally Ride, which is a brand new vessel in the U.S. research fleet. And this is where the in-situ pumps are being staged, and there's a whole big fleet of these pumps here to be used to collect particles throughout the water column down to, trying to think how deep they're going. They're going about a half a mile deep in the ocean this time, and so they're going to be out here for a month. And the ocean changes. Big scale sort of currents pass by, and the atmosphere causes eddies, and the nutrient systems can change as a result, so the community changes as a result. Being out here for a month, they're actually going to be capturing some temporal variability in the system. So the pumps are how we capture those particles. We put a bunch of them on the hydro wire deployed off the side of the ship. So these are the in-situ pumps that we use to collect particles deep in the water column. The ocean gets really cold after you move out of the surface layer. So for organisms that are living in the cold ocean and also where there's more pressure, we don't want to shock them. We want their natural signal. So by pumping in situ, we can achieve a few things like capturing that natural signal, but also getting more and more water, because if you had to pull that water up, you have to use a lot of energy and it would just be a lot more effort. So we really like these for getting really high quality samples. So we're capturing features like in the upper ocean, we're capturing a depth where we expect mostly phytoplankton or photosynthetic organisms. And then we're capturing sort of a transition into the deeper ocean where we expect there to be all of this heterotrophic activity that's respiring the carbon from those phytoplankton. And we're tracking that all the way down into sort of the darker, deeper ocean to see where that carbon has gone. How much of it has stayed in this particulate phase that sinks and could sink to the very deep ocean, and how much of it has actually been respired as CO2.
University of Hawaii's Sea Grant College program, focused on Hawaii's coasts and its communities through sustainable development, safe seafood supply, sustainable coastal tourism, hazard resilience, and healthy coastal ecosystems. Hawaii's Sea Grant.
Welcome back to Voice of the Sea. We're talking with marine chemist Ken Buessler about tracing carbon through ocean food webs.
I look at marine snow. So I don't know if you know the term, but all the little particles that settle from the top sink into the deep ocean. What they really are mostly pieces of the little plants and animals that have grown in the surface in the sunlight, and they sink down through the twilight, the darker part of the ocean. Another way to think of marine snow is like manna from heaven, right? If you're an animal, you need to eat this stuff. And so it's coming down, and you come up with efficient ways to eat stuff. There's more food, more things grow, right? That's how ecosystems work. Exports, this project, and my role is to capture those particles as they're sinking, and either measure directly what they're made out of, or indirectly measure the flow by doing isotope analyses that tell me something about how much snow is falling. We use sediment traps that are simply like a rain gauge. They capture stuff as it settles, and then you take that precious little sample and you bring it to your lab back home, and you do chemical analyses. I'm in the chemistry department. Carbon, nitrogen, silica, the major elements that are in our oceans, in our plants and animals. Think of plants, they take up CO2 from the atmosphere. If we got rid of all the ocean plants, the atmosphere would be much warmer, by 200 ppm. We're at 300 now. So they're doing a great service by taking some of that carbon dioxide as they grow into their bodies, just like plants do in photosynthesis, making organic carbon. And that sinking process, getting deeper, takes it out of contact with the atmosphere, reduces the CO2 in the atmosphere. How efficiently do they do that? Why is it different in one location or the other, one season and the other? That's the type of thing we're looking to gain an understanding on in exports. And I've never been on a ship with this many people measuring all of these different compounds, all these different linkages. So I'm measuring every flow, every arrow of carbon can go between this critter and that critter and sink at this speed or a different speed. You can actually start closing the box and getting really quantitative about those fluxes and what they mean and why they might be different this year in 2018 in the Pacific than what we hope to find in 2020 in different conditions in the Atlantic. The first place we're going to is one of these it's like the grass, right? It's the inefficient place. It's where most of the carbon just kind of recycles in the surface water because there's small cells, they don't get out very fast, and there are a lot of zooplankton animals that eat as much as being produced. We're going to move this to the Atlantic during what's called a bloom, springtime, when things are happening so fast that the animals can't keep up with all the carbon that's being produced. The cells are big, they're heavier, they're diatoms that have this silica that makes them sink fast. So we're going to see a completely different situation in the Atlantic, where most of the carbon during those few weeks is getting down below the sunlit surface layer, in through that twilight zone and below the top 500 meters, 1,500 feet, something like that. A lot of the motivation, as we've talked about, goes back to climate change. So we want to be able to tell you in 50 years how warm will it be, in 100 years. We need to understand the current ocean well enough to know how fast it's taking up carbon to make those predictions, and why some places are different than others. Some times of year, as we talked about, are different in their ability to remove carbon from the atmosphere and take it into these animals, make marine snow, and settle out. And so to make that prediction, we have to understand the current ocean better than we do today. So it's important to help inform all those decisions you might make about, should we move people away from the coastline? Should we build big dikes and hide behind them? How are we going to deal with the changing climate, sea level rise? All those issues are tied in some way to the ocean's ability to store carbon for long periods of time.
Next, Claudia Benitez Nelson and Stephen Pike share with us their working space, where they will process thousands of samples as they work around the clock.
This is Cafe Thorium. It's specially designed to accommodate all of the types of sampling that we do. So our filtration is just out that door, but we'll get our samples, we'll count them, we'll do our data analysis. We have our fume hood over here, our artwork, our espresso machine, our music, our car stereo, with a tape deck, by the way.
Oh.
So it's really nice because it allows us to just put everything in kind of exactly the places that we need. And we're going to be processing thousands of samples. So it's great that we kind of have our all set up and, our racks and got everything. It looks really super clean right now. It won't stay that way. We're using naturally occurring radioactive tracers to look at the timing and the magnitude of how those particles are making their way into the deep ocean. We use thorium isotopes, and thorium is really sticky. So if there is a particle out there, thorium just sticks right onto that particle, and then when that particle sinks, maybe it sinks slowly, maybe it sinks quickly, and we're able to track that thorium and get an idea then of where the particles came from and where they're going. We measure thorium-234, so that is a radioactive element that's produced from uranium-238. Uranium, when we talk about uranium, everyone thinks about, nuclear weapons, but it's naturally occurring. There's a lot of uranium everywhere, and in seawater, uranium naturally exists, and it's conservative, which means that it is not sticky. If you know what the salt content is in the ocean, you know what the uranium concentration is. It's that easy. But when uranium decays, it decays to thorium-234. Thorium-234 is sticky. And when thorium-234 decays, it takes about 24 days for it to, about half of it to decay away. And the thorium that's in that water, if there were no particles there, it would just sit there with the uranium. It would be very happy, just exist. But once the particles form, uranium stays, but the thorium sticks onto that particle. And then those particles leave. So then we'll measure the uranium there, and we'll measure the thorium that's left. And the difference between the two must have sunk out. I'm really excited because we are measuring everything that we can think of that is going to help us understand why material makes its way into the surface ocean, out in the middle of, Ocean Station Papa, way far away from land, and then literally what happens and how is it transformed from bacteria and viruses all the way up to like fish. And then it's moving, right? And the physics and the kind of the washing machine motions that move it down. You don't get to do that, right? I mean, it's complicated. It takes a lot of scientists to come together. We've all got to make sure we're all on the same page, and we're doing it. And so that's awesome. We have these little fancy paddles, and right now they're empty because we haven't collected any of our samples yet. But we'll collect our water and we'll filter it through a little filter, and we put the filter on here. And that's really all we do is we take the filter, we put the filter in here. You'll see there's 5 spaces for it. We'll take 5 filters, we'll put it in what we call our Reso beta counter. What we do is we put it in the counter, and this is our counting setup, and we literally have this instrument here, and if you look, you can see there's little red dots. So those red dots, that's the radiation coming from just around us, from cosmic rays, and it's like, you can hear it. And then this is actually the samples when the sample counts, and you'll see it'll flash green. It's not flashing green right now because we're just doing some background counts, so that's good that we have very little coming in. When we count our samples, you'll see the green flashes. This is our counter, so I said, we have those 5 spaces. Well, here's the 5 spaces, and this is for this counter, for this counter, for this counter. Every time the thorium decays, thorium-234, it's radioactive, it emits an alpha, or a beta, or a gamma. Thorium-234 emits a beta, and we just count it. Boom, boom. Thorium by itself, not so exciting. You measure thorium in the ocean, and people are like, really? That's okay. But what it can tell us about all the other processes and cycles, now, that's why it's cool.
Well, I'm a radiochemist by trade. I used to be a commercial fisherman. I like going to sea, and that was always something I enjoyed, obviously, as a fisherman. But the hours are a little better, and I don't smell so bad. To look at the ocean, the water all looks the same for the most part, but it's as different as terrestrial life. If you look at land from a satellite, you'll see the Sahara Desert, which is just a barren desert, but then you'll see the tropical rainforests, which are green and lush. And there are parts in the oceans that reflect that exact thing. The Caribbean is so crystal clear because there are no nutrients left. And so very little can grow in those waters, plankton and zooplankton, so that you can see forever. But where I'm from on Cape Cod, we get the spring and the fall blooms, and you might see 2 or 3 feet in front of you just because there's so much growing in the water. The science lets you see all that. You wouldn't see that without what we do here.
We are looking for a few heroes. mentors, trailblazers, innovators. A passion to change lives. Spark curiosity, open hearts, and awaken minds. Help students answer the question, who am I? This could be your calling, but this is no job. It's the journey of a lifetime. Be a hero. Be a teacher.
Welcome back to Voice of the Sea. We're exploring the use of color and light in understanding the marine food web with physicist Emmanuel Boss and biologist Colin Ressler.
What we're doing is we're calibrating, you want to pass me the next one? We're calibrating sensors that are going to be deployed on different platforms during the cruise. And what we want to make sure, they all got calibrated at the factory, and they got calibrated
by a specialty calibration
by a
facility.
specialty calibration facility, but we still want to make sure that they all agree.
And this is critical because this project is based on carbon, and a lot of that carbon is in the particulate form. And so these sensors are what we're using to track the particles.
This one is 035. So everybody from both boats gave us all their sensors to cross-calibrate. So this is really a community service project we're doing.
Sometimes the ocean's really bright, and that's because of scattering, and sometimes it's really green, and that's because of absorption. And so we measure the absorption and the scattering, as Emmanuel said. And so even a person who doesn't have these sensors can detect differences, and that's all related to the carbon that's in the ocean.
Depending on where you work in coastal environment or you work in the middle of the ocean, the particles you see are very different. And in the open ocean, they tend to a large degree not be organic. They're not inorganic particle. There's some dust, but it's a very small fraction of the total particle pool. While when you get to coastal environment with rivers coming in, you can have a lot of inorganics in
sediments
the water.
Coming from the rivers. And
this is the Oman.
Emmanuel is a physicist who's coming to biology. I'm a biologist heading to physics. And so, being flexible within your discipline and seeing the connections between physics and biology and geology is really critical. Yeah.
Technology is really important in oceanography. There's the moment you come up with a new measurement that nobody has measured before, you see the ocean in ways nobody has seen it, and you're able to say things about it that we were not able to say before. So there's several revolutions that happened in the last few years that are impacting this field. One is satellite with much smaller footprint. That's particularly in coastal environment. Now you can go down to tens of meters, where before you could only do kilometers in terms of water quality. So it's really, really exciting. Another one is electronics, the availability of these boards like Raspberry Pi and Arduino, which allow us to build sensors for much cheaper than we could buy them or get people to do them for us. And the third one, which is big time on this cruise, is microscopy, automated microscopy. So we have cameras that are going to go down with a CTD rosette, taking picture 15 times a second of gelatinous zooplankton, copepods, a lot of the larger predator that beforehand you could not catch them with nets. You'd break them. So with these cameras, we're now able to see where they are, how much of them there are. We're done.
Can I ask you, what is the device you're working on?
This is called an imaging flow cytobot. And it's a lot like a microscope that has water flowing through it. And it has this incredible way of aligning the sample so that particle goes through almost individually. And then it takes a picture of every single particle that goes through. And there's some nice software that then allows you to classify those in terms of phytoplankton and non-phytoplankton particles. And so it allows us to know who's in the water. It's making the connection between what's in the water and how much carbon is associated with them, and their optical properties that can be detected from satellite. And so we're trying to find the relationship with when we see a community of phytoplankton, and then we can measure their absorption and scattering properties. We can link that directly to the color of light coming out of the ocean, which is detected from satellite.
So NASA insists that all the scientists it funds, within a year, all their data has to be publicly available. And
it's beautiful.
Yeah.
It's beautiful for teachers, it's beautiful for students, it's beautiful for just people who are interested in science and the ocean. And that's been a huge cultural change since Emmanuel and I started, is the availability of data. I mean, we just make our data available. In the old days, people would be like, well, what if someone writes a paper with our data? And now it's like, please write a paper with my data. So
I
if
have more than I can
you make
digest.
your data available, and then someone in another country can put it all together and ask a question that never even dawned on you. And they can solve a problem because you have provided data, Emmanuel's have provided data, and they put it together in a completely different way of thinking. And so it really democratizes science. You don't have to have $1 million worth of instrumentation. You just have to have access to data sets. And that, I think, is revolutionary.
Yeah. We tend to bias our view based on the data we have at hand. And the moment you add something different, you say, oh, wow,
yeah,
it's not what I thought.
yeah,
There's something different,
Yeah.
exactly. It's a really good time to be a young scientist. There's just a ton of new things happening. It's not that we're not trainable and cannot learn new things, but we're still so much used to the old things that there's a lot of room for young talent to come and do amazing new stuff.
Next, graduate student Chelsea Lopez shows us what the next month of her research will be like, collecting water samples and living aboard the Sally Ride.
Well, I'm a graduate student at the University of Miami, and I'm a second year, going into my second year of my PhD program in ocean biogeochemistry.
Oh, wow. And what is your particular research about?
My research is on dissolved organic carbon. So I collect vials of water out on these cruises to analyze back at the lab. We'll analyze total organic carbon, dissolved organic carbon, as well as total nitrogen, and get levels for that.
What is dissolved organic carbon?
Yeah, so it's kind of something that's still being characterized. So any organic molecule in the ocean that is below 7 microns. So we do filter them, and that would be whatever goes through the filter is considered dissolved, and anything that lands on the filter would be particulate organic carbon. So there's a lot of like polysaccharides, amino acids, things like that that come from the biology in the ocean that get broken down to a certain point, and we'll collect those and analyze the levels for that. We will measure these back in the lab after the cruise is over, and so you can see where the hot spots are and what has higher concentrations and lower concentrations, and see where the biology is taking place. We will take these little vials out, so they're just 40 ml vials that we have here, and so I'll take them out to the rosette when it comes up, those big bottles that they pull up from underwater, and then there's a little spigot, and then I'll just fill them right up.
And so you'll do that kind of immediately, and then you'll take this sample back with you to the University of Miami.
All of the 2,600 that I brought with me will be shipped back.
Wait, say that again. You brought 2,600
Yeah,
vials?
there's 2,600 vials, and I'm hoping that maybe I'll fill all of them, but we'll see how much time I have.
Is this your first cruise?
This is my second. So I went out last month, actually, on Line P in the same area. It was a lot of fun. It's a lot of work and not a lot of sleep. You make a lot of friends and build a family, which is really nice, even in a short period, because you're living with these people. You learn a lot of new things from people. You get to see, the experts do what they love, and it's just one thing to read about it and another thing to see them do it. And I think you learn a lot more from doing that, which is a lot of fun. Yeah.
In our next episode, we catch up with researchers on board the research vessel Roger Revelle, who will explore alongside the Sally Ride in the Exports mission to unlock the mysteries of the carbon cycle. Mahalo for watching, Voice of the Sea.
The University of Hawaii Sea Grant College Program, helping coastal communities of Hawaii and the Pacific through research, education, and outreach. Serving the community, from elementary to graduate students. Hawaii Sea Grant.